we've done since our VLDB-08 paper, we've been looking at output perturbation techniques where instead of publishing a graph, you, as the data owner, receive queries and respond to queries with noisy answers. This has some limitations. For example, with ease of use is not so good because, as I said, it's difficult to decompose a data mining task into a set of small set of queries. And we'll come back to that. But the advantage is that we can have very formal privacy guarantees and very and precise bounds on the accuracy, and the scalability is quite good because all we have to do is compute the query answer and add some random noise. Okay, so let me go into some more detail about output perturbation as a technique. We're going to use output perturbation techniques that are designed to satisfy a notion of privacy called differential privacy. This has been in the literature for a few years now, but there are comparatively few results for analyses involving graphs. So the basic idea, as I said, is you compute the true answer and you add random noise. So I'm going to go into some more detail about differential privacy. Does anybody have any questions at this point? Yes?
I was a little puzzled by the ways you were trying to protect information, including randomized ages.
Yeah.
You started with a graph. It looks like you ended up with an entirely different graph. If there is no way of going back, then what analysis that you do when the new graph is going to be happening to the original one?
Well, that's something that is typically in these works measured empirically. So we would apply anonymization on a data set, and then we'd try to do a bunch of analyses. Like we could run a disease transmission study on the original graph, and we could run a disease transmission sort of simulation on the anonymized graph and look at the difference between the findings that we would derive. And there will be a difference, and that difference is the information loss as a consequence of the privacy, and it may depend on the privacy parameters and stuff like that. But one of my points here is that it's difficult to say with a lot of these techniques that if I apply anonymization with this privacy parameter, I will not have information loss worse than this. I'll have a bound. And that's one of the limitations of the technique. They tend to kind of transform the data until some structural criterion is met, do a certain number of edge additions or deletions or cluster nodes together in groups of certain size. And for different data sets, that may result in very different levels of distortion for different analyses and stuff like that. Okay. So I'm going to move on to differential privacy. So the intuition behind differential privacy is that the output of a differentially private algorithm will be indistinguishable whether or not a specific sensitive fact is present in the database. So if you're worried about disclosing your sensitive fact, you have the assurance that the answers that the mechanism is providing will not reveal anything because they're statistically indistinguishable. So the idea here, imagine we have a query and we think about numerical queries, so like a counting query that's going to count the number of nodes with degree 3. And imagine for the moment that our sensitive fact is the edge between Dave and Ed. I'm just worried about protecting that edge, disclosing that edge. So I can imagine another data set where I remove that edge completely. Well, now my mechanism needs to give an answer to the same query for that data set, and the intuition or the basic idea behind differential privacy is that these two answers will be statistically indistinguishable. So in the first case, on this toy example graph, the true answer to the query is 0. And I add noise and I get some answer P. On this other data set, which is called a neighbor because it differs only by one edge, the true answer is 2. I add some random noise to that and I get the answer Q. So we want these to be indistinguishable outputs, and in that way we have a guarantee that we've protected the existence of this one edge. All right? In fact, we want the output to be indistinguishable across any addition or removal of an edge. So the formal definition is shown here. An algorithm that satisfies differential privacy has to be a randomized algorithm. And it provides epsilon differential privacy if, for all pairs of neighboring graphs, graphs that differ in one edge, and any set of outputs, the probability of getting the output S on one of the neighbors that probability is close to getting that output on the other neighbor, which results from removing an edge. And it's close. What I mean by saying these probabilities are close, they're close by this factor e to the epsilon. Epsilon is a privacy parameter. It's usually a small number, like 0.1. If epsilon's 0.1, then we have e to the epsilon as about 1.1, and we've kind of bounded the difference in these probability distributions. If we lower epsilon, make that number smaller, we bring the probability distributions together, we require that they are closer, and we enforce stronger privacy. Okay, so that's a formal definition. I'll give you some examples. Well, actually, no, I'm going to talk about the mechanism. So that's a definition, that's a privacy notion that is persuasive because it allows this intuitive notion of opting out of the database. It should provide almost as good privacy, subject to the privacy parameters, as if you weren't in the database at all. And it doesn't make any assumptions about the power of the adversary or their background knowledge. So in addition to this definition, the original work also provided a construction which satisfies differential privacy. So a way of designing algorithms, a way of answering queries that satisfies differential privacy. So here's the basic idea. We compute the true answer, which is Q, evaluated on our data set or our graph, G, and we add a random sample from a special distribution. It's the Laplace distribution. It's a symmetric exponential distribution. Its mean of the Laplace is 0, so that the mean of the output is the true answer. But there's some variance around that output, which is controlled by this B parameter. So let me show you an example. When on the last slide, I had this sample query, number of nodes with degree 3. The true answer to the query was 0. So if I'm going to output an answer, I'm going to add random noise, and I'm going to draw a sample from that red line on the left. It's centered around 0, and it's got some variance, right? Now, if I am instead answering the same query over the neighboring data set, for which the true answer was 2, then I would be sampling an answer from that gray line. And the definition of differential privacy says that those distributions can't be too different. And I'm worried about the maximum difference. The maximum difference is indicated by that yellow line on those graphs. The probability of answering 2 on the first database is rather low. It's the red point. The probability of answering 2 on the other database is rather high. That's the difference. That needs to be bounded, subject to my privacy parameter epsilon. If that yellow line on the left is too big, it's bigger than I want it to be, that's a kind of policy decision about how big I should allow that to be, then I'll change the scale of the Laplace distribution. The Laplace 1 distribution will go to a Laplace 2 distribution. That means that the distribution's fatter, there's more error introduced, but that yellow maximum difference between the distributions has been reduced. And so we provide more privacy by increasing the scale of the Laplace distribution. In fact, what we need to scale the noise to is these two parameters. The privacy parameters in the denominator. So if it's a tenth, then we multiply the scale by 10. But in addition, we have this measure called the sensitivity of the query. The sensitivity of the query measures how much the answer can change, answer to my query can change over neighboring databases. It's basically how much I might have to move those, the distributions, they might have to slide over neighboring databases. So I'll define that formally. The sensitivity of a query, it's a property of a query. It has nothing to do with the particular database, particular graph I'm looking at. It's a static property of the query, which is defined to be the maximum difference over any two neighboring graphs in the value of the query. Okay, so let me make this concrete. We've got a query like the degree that asks for the degree of a node A, some identified node. I say, what is its degree? Sensitivity of that query is 1. Why? If I add an edge to a graph, I change 2 degrees, each by 1. Well, one of them could be the node A, and that degree would go up by 1. But I could never add an edge and cause A's degree to go up by more than 1, or delete an edge and cause it to go down by more than 1. So the sensitivity